This is another important derivation from optics. When two thin lenses are placed in contact, what will be the effective focal length, power, and magnification? So lens 1, principal axis. The assumptions for lens maker's formula and refraction at spherical surface. It's valid for this derivation also. Object is point size and is placed on the principal axis. The lens is thin, thickness is very less. So the first light ray will go normal to the lens along the principal axis without any refraction. Second light ray incident on the lens, since it's a converging lens, bend towards the principal axis and meet with the other light ray at eye to form the image. The object distance and the image distance. Object distance is u, image distance is v1. This is by lens 1 of focal length f1. This is formed only if the second lens is absent. To bring the second lens, now this light ray cannot go straight. After the first lens, it again passes through another refracting medium, the convex lens 2. Since it's convex lens, it again will converge once more and form another image, which is a final image at a point closer than I1 to the lens. The first lens, this will act as the object and object light ray. For the second lens, this light ray will act as the object light ray. Or virtually, you can take the image formed by the first lens, act as a virtual object for the second lens. This light ray cannot go, so it's now an imaginary light ray. Lens 2 is placed. So another refraction will make the light ray bend more and form the final image at eye. So that will be the image distance for that lens. P. This is the image formation for both the lenses together, forming the final image at eye. Now, as a part of derivation, assumptions, object is point sized and placed on the principal axis. Both the lenses are assumed to be thin, so that distance measured from center of the first lens or center of the second lens or from their common center all treated are to be equal. So u, v, v1 all are measured from the common center or from both the lenses will be equal. Now the first lens forms image at I1 if the second lens were absent. So if you apply the lens formula for the first lens, 1 by v minus 1 by u equal to 1 by f. F is f1. Object distance is u. For the first lens, the image distance is from the lens to I1, which is v1. So 1 by v minus 1 by u becomes 1 by v1 minus 1 by u equal to 1 by f1. Now the image light ray of the first lens act as the object light ray for the second lens. For the image formed by the first lens act as the virtual object for the second lens. That means image distance of the first lens act as the object distance for the second lens since they are placed in contact. So u for the second lens will be v1 and the final image is formed at v. So the image distance will be v. So 1 by v minus 1 by u becomes 1 by v minus 1 by v1 equal to 1 by f2. So if you add the two for the total refraction, 1 by V1 minus 1 by V1 get cancelled on left side. So 1 by V minus 1 by U equal to 1 by F1 plus 1 by F2. Now, if the both lenses are replaced by a single equivalent lens of focal length f, for the same object distance, it will form image at same image distance as the two lenses together. So for that lens, we can write 1 by f, the equivalent focal length equal to 1 by V minus 1 by U. This is for the equivalent lens, image distance, object distance, the focal length is f. If you combine 3 and 4, you get f side is same. So 1 by f1 plus 1 by f2 equal to 1 by f. So that is the effective focal length. Reciprocal of the focal length equal to sum of the reciprocals of the lenses. In terms of power, P equal to P1 plus P2. If you check the magnification part, for the first lens, magnification is image distance by object distance. V1 by U is the M1. For the second lens, magnification is image distance by object distance. Image distance V by object distance. So V by V1. Product of M1 and M2, V1 by U into V by V1. V1 get cancelled, only M1 by M2 equal to V by U. Now, if you find the magnification for the effective lens, equivalent lens, its image distance by object distance V by U. So for the equivalent lens, magnification is V by U. Both together, it is V by U is M1 into M2. We combine A and B, we'll get the effective magnification will be the product of the magnifications. Now, these two formulas are valid with proper sign conventions. For converging lenses, F and P are positive, and for diverging lenses, F and P are negative. So the same formula is valid for both converging and diverging lenses, only suitable sign convention to be applied.